introduced the TCP segment. So when TCP sends segments across the internet, they're structured like this. They have some header and some data, some optional data. Not all segments contain data. For example, setting up a connection, these SYN segments do not contain data. The type of segment, when I talk about a SYN segment, an ACK segment, a FIN segment to finish, the type of segment is indicated by which flag is set. Some 1-bit values to indicate what type of, or what's the purpose of this segment. So the flags. We have source port, destination port, a sequence number and an ACK number. Sequence number to indicate the sequence of the data we're sending, and an ACK number to indicate we're acknowledging some data that's been received. You'll see in the final exam, in the hints, the structure of the header formats are given. So you don't need to remember what these fields are, but given this picture, for example, you should be able to know, you should be able to calculate what's the typical size of the header. For example, I say that a TCP segment is 100 bytes in length. Then how much data is in that? Well, you would assume that the typical header size is 20 bytes, assume no options. If the total segment is 100 bytes and the header is 20 bytes, then the data is 80 bytes. Okay? So you should be able to use the header information to answer some questions, not just for TCP, but for IP and other protocols. What we got to last week was how to set up a connection. And we said that we have this three-way handshake, a SYN, a SYN-ACK, and an ACK. That is 3 TCP segments exchanged between the client and the server. And one purpose of this exchange is to synchronize the sequence numbers they're going to use for their data transfer. So TCP uses 32-bit sequence numbers, and it's used for different purposes, basically to keep track of the data that's been sent. We need that for error control, so that we know what data to retransmit. If I send a lot of data to the server, and the server recognizes something's gone wrong and it's missing some data, then the server may send back an ACK to indicate to the source to retransmit some of that data. Which data to retransmit? Well, we'll use sequence numbers to indicate which data to retransmit. Flow control makes use of sequence numbers. We use sequence numbers to know how much we're allowed to send such that we don't overflow the receiver. And although we will not go into it, congestion control uses sequence numbers as well. So when we send our segments, they contain some sequence number to indicate the order of the data that's being sent. We'll go through and see how they work shortly, but when we establish a connection, each side chooses an initial sequence number, an ISN, and they're independent in that, remember when we set up a connection between A and B, let's say A initiates the connection to B. So we have some three-way handshake. We'll go through the steps. Once the connection is set up, it doesn't matter who initiated it. Either A or B can send data. It's a full duplex connection. So A can send data to B, and similar, B can send data to A. And they use independent sequence numbers to do that. That is, when A sends data to B, it starts with its initial sequence number, whatever the value it chooses, and it will increment that as it sends more data. And when B sends data to A, it has its own independent initial sequence number, and as B sends data to A, it increments its sequence number. But they're independent, okay? So we have basically two sets of sequence numbers, one for each direction. The ISN does not have to be 0. Okay? When I start a connection, it's not necessarily 0 and 0. Both sides get to choose their initial sequence number. Why? Well, it's useful in that we can, when we have previous connections, that is, I've created a connection from A to B, transferred some data, then I close that connection, and then sometime later I create a new connection from A to B to transfer some more data, then it's useful to use a different sequence number that was used in the previous connection. So that if there are some old packets or some errored packets that are duplicated somewhere in the internet, if we receive them from the old connection, we can discard them. So TCP allows each side to choose its own initial sequence number, not necessarily 0. One common approach is to choose a number that is greater than what you've used in the previous connection. So the operating system keeps track of what you did in a previous connection, and in the new connection chooses an initial sequence number greater than that previous one. So they may be different, and especially non-zero. And therefore the idea of the connection establishment is to tell each other which initial sequence number you're going to use, agree upon them, to synchronize them. The other thing for the connection establishment is to let the other side know that you want to transfer data. For example, to allocate resources. If B is a web server, A initiates a connection, and that informs B that A is about to transfer data. So B could allocate some memory, some buffer space to store that data it's going to receive and to record information about the connection. So setting up a connection is to synchronize the sequence numbers and to allocate resources in preparation for sending and receiving data. And what we covered last week was how it works. How do we set up the connection? We call it a three-way handshake. There's SYN, SYN-ACK, ACK, 3 TCP segments, but they have different purposes. We will not go into it, but why do we need 3 messages? Well, it turns out if you just do 2, or say one in one direction and a response, like a SYN and an ACK, then there can be some confusion if there are some duplicate or some error segments in the network. So there's a good reason why there's this 3 messages exchanged. The textbook has some examples of what happens if you didn't do a 3-way handshake but just one, or a 2-way handshake. Say a SYN and an ACK. It doesn't work in some cases. And this is what it looks like and what we saw in a more specific example last week. A initiates the connection by sending a TCP segment with a SYN flag set, and in particular sets the sequence number to the initial sequence number A chooses to tell B. B receives that. If everything's okay and it wants to accept the connection, it records the initial sequence number of A, chooses its own initial sequence number for B, a potentially different value from what A chose, and sends back a TCP segment. This segment has 2 purposes. One is to tell A of its initial sequence number. So we set the SYN flag and we set the sequence number to the value B chose. And the second purpose is to acknowledge the value A chose. A chose a value, told B, B sends an ACK, that is, it sets the ACK flag to true and sets the ACK number, the acknowledgement number, to the value that A chose plus 1. Because normally our acknowledgements indicate the next value expected. So it's plus 1 in this case. The third message in this 3-way handshake is A responds with the final ACK, saying, thank you, I accept the value you chose, and here's the ACK, and with ISN of B plus 1. Once that's complete, then they can exchange data. And the sequence numbers that they start with, for the data that they send, A starts with ISN A plus 1, and B starts with ISN B plus 1 in general. We'll see some examples of that in a moment. there's an option. That is, this is the normal, or the default procedure, SYN, SYNAC, ACK, and then send data. It turns out that an option may be to, on this last ACK message, to include some data there. So we piggyback some data on this ACK. Because often, if A initiates the connection to B, A wants to send data to B. So to draw that, the default approach would look like this. SYN, SYNAC, ACK, and then another TCP segment from A to B containing some data, the first piece of data. But we can combine these two together. That's piggybacking. Send one segment, but it has two purposes here. The data that A is sending to B, and also the ACK that A is sending to B. It would look like this. SYN, SYNAC, and then that last message in the three-way handshake also contains some data from A to B. Why? It saves on transmission time. Here we transmit just one segment, here we transmit two segments. In particular, here we transmit two TCP headers, because each segment contains a TCP header. In this case, we transmit just one TCP header. So there's some saving, small enhancement in performance by including some data in that last ACK. It's called piggybacking, in that we combine the ACK and the data together. It's possible in TCP. Assume, unless I state otherwise, the normal approach of SYN, SYNAC, ACK, no piggybacking. So there are some options in TCP that can improve upon performance. We can close, once we transfer data, we need to close the connection. And this shows a quick example that we use these fin segments. We set the fin or finish flag to be true to indicate A wants to close the connection. That is, A has no more data to send to B. A sends a fin segment to B, B sends back an ACK saying OK. Similar, or a little bit more complex in that both sides can choose to close the connection. When A has no more data to send to B, it closes the connection or sends the fin segment. But it's still possible for B to send data to A. A sending this fin segment means A has no more data, but B may still be sending data to A. And it's not until B sends the fin segment to A, so B is finished sending data, and then the ACK, and then the connection can be closed. So it's possible to have what's called a half-open connection or a half-closed connection. That is, one side's closed it, the other's still sending data. And there are many other combinations of how to set up a connection, how to close the connection. It gets quite complex because the fact that one can close and the other may have it open. If things go wrong and packets are lost or there are reset type messages, then the different options available become quite complex then. We will not go through those. Simply know the three-way handshake and the fact that we also need to close the connection when we're finished. What we want to focus on is how do we send the data. How do we, once we've opened the connection with a three-way handshake, how do we transfer data? Any questions on the three-way handshake, setting up a TCP connection? SYN, SYNAC, ACK. Remember them, you'll see them quite often. Okay? No problems? TCP is what we call a connection-oriented protocol. It's a protocol where we set up a connection. So the concepts are similar to virtual circuit packet switching, but it's different. Remember, packet switching is about how we deliver data through the network. It involves the intermediate routers, the intermediate packet switches. TCP is an end-to-end protocol. It's only between the source host and the destination host. The routers that forward that data have no idea or don't care that it's TCP sending data through there. So from TCP's perspective, there's no involvement of the intermediate nodes. But this concept of before we send data, we set up a connection is similar to the concept of virtual circuit packet switching, which is before we send our data, we set up a connection. So the concept is the same or similar. And other protocols may use this concept as well. But we would not say that TCP is virtual circuit packet switching. We generally say it's connection oriented. We set up a connection. The concept of setting up a connection is the same in virtual circuit packet switching, in circuit switching, and in TCP. We'll see an example in Wireshark, and you've seen it in your assignment shortly. How do we send data once we've set up a connection? TCP has algorithms or mechanisms for error control, retransmission. We'll see some basics of we send data, we expect an ACK to come back. If we don't receive it within some timeout, we may retransmit. We've seen those schemes before in our stop and wait and go back and ARQ mechanisms. It has algorithms for flow control. The source cannot send data as fast as possible. There's some limit as to how much data it can send so that we don't overflow the receiver. And we've seen the general mechanisms just after the midterm of the stop and wait flow control and sliding window flow control. TCP uses a sliding window mechanism. It can send a set of data, a sequence of data, and then must wait until it starts to receive an ACK, and then it can send more data. And it also has congestion control, again some way to control how fast it sends so that it doesn't overflow the routers. We'll just go and give an example of how error control works. In all of these we use sequence numbers, so we'll come back to them in a moment. Some of the details of how these algorithms work depend upon the different implementations. So it's up to the operating system implementation to choose the details. For example, Windows, or one version of Windows, may do it slightly differently from a version of Linux or a Mac operating system. Okay? So some details can be chosen by the implementer. Like when to send data. We'll see that there are different options. You don't have to, TCP doesn't have to send a segment as soon as it receives data from the application. It may wait. And when to send an ACK. Normally we think we send a data segment and then the receiver would send back an ACK segment. But we don't have to have one ACK segment for every data segment received. We could send 3 data segments and then the receiver sends one ACK back acknowledging all 3. So there are different choices there. TCP offers what we call a stream-oriented data service. Our application generates data, delivers it to TCP. TCP treats that data from the application as just a stream, a continuous stream of bytes. It doesn't treat the messages from the application as separate messages. The best way to describe that is with some examples. Let's try and illustrate how the different options TCP has of treating data. So remember TCP sequence numbers, 32-bit values included in the header, and the initial sequence number is synchronized in the three-way handshake. Let's say we've set up a connection and we want to transfer some data from A to B. We've done the three-way handshake, SYN, ACK, ACK, and we want to send data from A to B. And just for our example, let's say A chose an initial sequence number of 300. B chose an initial sequence number, but let's, for this example, focus just on A to B. So the initial sequence number of 300 chosen by A would be included in the first SYN segment, and the ACK that comes back from B would be saying, thank you, I accept this value of 300. The next value expected is 301. That's in the connection setup, the first phase. And then when A sends data, the first piece of data it sends, the sequence number will be 301. Okay? The initial sequence number plus 1. Do not draw the diagram I'm about to draw. It's an old one from when we looked at flow and error control. What I draw is when we had sliding window, one data segment, a second data segment, and so on, and then an ACK would come back, and what we've always said is the ACK number is the next number expected. So if we send data segment with sequence number 1, the ACK would come back with ACK number 2, saying, thank you for sequence number 1, I now expect 2. And when we send data segment with sequence number 2, the ACK would come back with ACK number 3. And when we send data segment sequence number 3, the ACK would come back with ACK number of 4. Okay? So the next value expected. That's what we've covered when we looked at flow and error control. TCP is not quite the same. Here we use sequence numbers to count segments. This is segment or frame number 1, and hence sequence number 1. Frame or segment number 2, sequence number 2, and 3. TCP uses sequence numbers to count bytes, not segments. That's the important difference to recognize. And that's what our slide tries to illustrate. Because when we send a data segment, we may contain multiple bytes. If we send a data segment with sequence number 301, the ACK that comes back does not necessarily contain ACK number 302. What it contains is an ACK number indicating the next byte expected. And we'll try and demonstrate that with some examples. So let's illustrate how TCP counts bytes using sequence numbers. What the example on the slide shows is a case where an application generates 10,000 bytes of data. So the application at A wants to send 10,000 bytes of data to the application at B. We've set up a connection already. We've chosen an initial sequence number of 300. The application delivers that 10,000 bytes of data to TCP. Now it's the job of TCP to deliver those 10,000 bytes across the internet. The conceptual way to think of how TCP uses sequence numbers is that each byte gets a sequence number. The first byte would be sequence number 301. Why 301? Because A chose an initial sequence number of 300 here, and the ACK that came back was 301, saying B expects the first byte to be 301. The second byte of data we could label number 302, and so on. So of those 10,000 bytes, the last byte we could think it is sequence number 10,300. So we count bytes in TCP, not segments. The way TCP sends that data is usually up to the specific implementation. It doesn't have to send all of that data in one segment. So it has 10,000 bytes to send. It may break that into multiple segments. And we'll see in another example, it may wait for more data before it sends. So it doesn't have to send all of this data at once. In the example I've shown on this slide, let's say that TCP decides to send that in 4 different segments. It's a little bit of an artificial example in that it's unlikely to happen like this, but it just illustrates how we use sequence numbers. TCP decides of this 10,000 bytes, let's send it in one segment that contains 1,000 bytes, in a second segment that contains 1,000 bytes, and then 2 more segments, each containing 4,000 bytes. That's up to TCP how to split that up. Then, so that's continued on this slide, the same case. We've got 4 pieces of data now. Then think if we think about the sequence numbers used here, we still have 301 at the start, 302, 303, and so on. The first byte in segment 2 has sequence number 1301. Now when TCP creates its segments, it takes the data, attaches a header, this H in this slide, and then we'll transmit that segment across the internet using IP. So this segment of 1,000 bytes of data plus a TCP header will be transmitted or sent to IP and then eventually sent across the internet to the destination as one IP datagram. The second 1,000 bytes of data will be put into another TCP segment. So we see the header attached and then delivered across the internet. So we can think we've got 4 IP datagrams that are going to be sent across the internet. Each are TCP segments. So they all have their own header. And importantly, the sequence number in that header is the byte number, or the number of the first byte in that segment. Let's draw it again on the board. This is our 10,000 bytes. We've divided it into, it's not really to scale. We've divided it into 4 chunks. The first one has 1,000 bytes. So does the second. And the next 2, 4,000 bytes. Again, how we do that is up to TCP. It may divide it into equal sizes. It depends upon, or the way to split depends upon performance or impacts on performance. So this will become our first TCP segment. We'll take 1,000 bytes of data and attach a TCP header, and inside that header we'll set the sequence number. This was 301, the last byte 10,300 because we label each byte, or we conceptually label each byte. The sequence number included in the header is the sequence number of the first byte in that segment. So the first byte here is 301, so the sequence number in this header is 301. For the second segment, we attach a header and set the sequence number to what? you need to count through. Okay, if the first segment has 1,000 bytes, we'd say from 301, 302, 303, and the last byte here would be 1,300. From 301 up to 1,300, there's 1,000 values. So the first byte in the next segment would be 1,301. And hence that's the sequence number included in the header. And so on. And that's what we get on the slide here, that the sequence number in the header of the third segment, 2,301, and in the fourth segment, 6,301. So note that the sequence numbers are not incrementing each segment, they're incrementing each byte. And the sequence number we include in the header is the sequence number of the first byte of data. So that's different from what we've seen in our previous examples of flow and error control. But that's how TCP works. This is an example where TCP chose to take that 10,000 bytes and send it as 4 segments. Any questions on how the sequence numbers work? That's important to understand the next parts of TCP. And it's a common point of confusion for students. Why? So in our example, why have we started with 301? In this example, in the connection setup, A has chosen an initial sequence number of 300, tells B, B sends back an ACK saying, thank you, the next value I expect is 301. There's no data yet, but that's how the ACKs work, the next value expected. And so the first piece of data starts with 301. The first data segment starts with sequence number 3, or has sequence number 301. If we try and draw this a bit clearer on those 4 segments, this is a data segment. Sequence number is 301. There may be an ACK, but for, well, let's say there's an ACK. What do you think the ACK number will be in this case? 302. No. What do you think the ACK number will be? B has received the first data segment. 1,301. The same way that we count bytes, we acknowledge bytes. So the first data segment, sequence number 301, contains 1,000 bytes of data. B receives it, and B has received 1,000 bytes of data. If we wrote down those bytes, it's received successfully 301, 302, 303, up to 1,300. That's the first 1,000 bytes in terms of sequence numbers. So B sends back an ACK with an ACK number saying, I now expect 1301. That's the next one expected. And in fact, our next segment, next data segment, 1301, and the ACK will come back with, what is it? 2301. Because this data segment contains 1,000 bytes, and the first one is 1,301, the last one 2,300. Yep.
The value of the ACK that A sends to B.
The value of the ACK that A sends to B, that depends on what initial sequence number B chose.
So it doesn't have anything to do with what?
It doesn't have anything to do with these numbers. It's independent, it's separate So imagine we're doing the same thing in the opposite direction, from B to A. We have our own set of sequence numbers. I haven't shown it in this example just to keep it simple. So not shown is that B would choose its initial sequence number, let's say 10,000, and the ACK would indicate 10,001. And when B sends data, it follows the same approach. Do we have a diagram that shows that? Here. This shows just the data transfer. I've drawn the first two, the data, the ACK, the data, and the ACK, and then the last two. So the third segment, sequence number 2301, it contains 4,000 bytes of data. When B receives that, it successfully received 2,301, 2,302, and 4,000 bytes, goes up to 6,300. So sends back an ACK with ACK number. I now expect 6,301. And then the fourth segment. And at that point, all 10,000 bytes have been received by the destination B. So that illustrates how sequence numbers are used in TCP. And also illustrates how our ACK numbers work. We send our data, we expect an ACK to come back to say, thank you, I've received the data. If we don't get an ACK, we'll see shortly that we may have to retransmit. One more example. Any other questions on that example? So you have to remember with TCP we count bytes, not segments. Our sequence numbers count bytes. And once you remember that, then the same concept as before. We send our data and our ACK indicates the next byte expected, not the next segment, the next byte expected. Try a different example. The example we showed was the case where the application had 10,000 bytes of data to send. TCP decided to break it into 4 segments. Let's try a different case. Let's say we've set up our connection already, and initially the application has 100 bytes to send. And what I show on this diagram is the application delivers 100 bytes to TCP at the source computer. TCP doesn't have to send that data immediately. It may wait some time. Let's say a short time later the application has some more data to send, 200 bytes. So it's possible that TCP receives 100 bytes and makes a decision. I've got 100 bytes to send to B. Let's wait a little bit longer and see if there's some more data to send. Because it's more efficient to send one large segment than many small segments. So in this example, let's say TCP receives 100 bytes and says, let's not send yet, let's wait. Receives another 200 bytes and then makes a decision, okay, I have 300 bytes to deliver, let's transmit now. So we send now a data segment, a TCP segment containing data. Let's say the initial sequence number chosen by A was 416. We haven't shown the setup of the connection, but let's say the connection was set up. This is the first piece of data. What is the sequence number in this TCP segment? For 417. Remember, with TCP connection set up, you choose an initial sequence number. The other side says, thank you, I now expect the next value, one more. So if the initial sequence number is 416, the first piece of data will be 417. And let's say that it's not a header field in TCP, but we can determine the length of this data is 300 bytes. TCP combines the two messages from the application into one, because TCP is a stream-oriented service. It doesn't care that they're two separate messages. It just treats them as sequences of bytes. So if we drew that, let's say there were 100 bytes that came from the application, and then sometime later 200 bytes. From TCP's perspective, it's just 300 bytes. This split between the 100 and 200, TCP doesn't care. It doesn't care that they're two separate messages. All its goal is to deliver that data across the internet. So in this example, TCP at computer A combines the two messages, creates one TCP segment, and sets the sequence number to 417. Eventually, an ACK comes back, and the ACK number, the ACK flag is set, and it contains an acknowledgement number of 717, because there's 300 bytes. The first one is 417, it would go up to 716 would be the last one, so therefore the next should be 717. So note the ACK number depends upon what the sequence number is, the first byte, and the length of the data in that segment. And then you can work out the ACK number. And from the perspective of B, TCP at the receiver delivers 300 bytes to the application. And this can be a bit strange, or at least from a programmer's perspective. What happens at the source application, it generated 100 bytes. Maybe a user clicked on a button at the application at the source. It generated 100 bytes to send across the internet. Then the user clicked on another button shortly later, which generated another 200 bytes. TCP sends all of that in one segment and then delivers 300 bytes. It doesn't split it back into 100 and 200. It simply delivers 300 bytes of data to the application at the server, in this case. So it's up to the applications to deal with this. You cannot guarantee that if we create two messages at the client, it will be delivered as two messages at the server. It may be combined. I think next semester in the lab you'll do a little bit of programming, or you'll see some source code to see how that works with TCP and application interaction. So it becomes quite complex into making sure your application can deal with this case, that there's not two messages here but just one. They're the main parts of how we use sequence numbers in TCP to deliver data. We have data, we have ACKs. The data contains a sequence number indicating the first byte, and the ACK number indicates the next byte expected. Any questions on how we use sequence numbers? What's next? Let's look at one example from Wireshark. This is a capture that I did, in fact, at the start of the course. One of the first Wireshark captures. And I've filtered many packets just so that we have some TCP segments, and it's a capture of accessing a website. So HTTP is involved. It's very similar to what you saw in your assignment, in the capture in the assignment where you captured web browsing. Most of you in your answers drew the TCP connection setup, and some of you drew the ACKs. So we have seven TCP segments here. The first three are the connection setup. We have if we look into the details here, we'll see it's a TCP segment, and it gives us in the summary info, it indicates it's the SYN segment, that is the SYN flag is set. We'll look at the details of the sequence number in a moment, but in general the response, so this is from my computer to some server. The server responds back with a SYN-ACK segment, and then my computer responds to the server with a third, which is the ACK. So that's our SYN, SYN-ACK, ACK, our connection setup. Once that's done, my computer, 251, sends to the server some TCP data. And in this example, the TCP data is a HTTP GET request because I was accessing a website. So the fourth packet here is TCP data, where the data is the HTTP message. The fifth is an ACK. I send TCP data to the server. The server sends a TCP ACK back saying, thank you, I've received that data. Packet number 6 is some data from the server to my computer. The data, in fact, is a web page. And the last message here is the final, is a TCP ACK. Let's look at some of the details if we expand. We can see the sequence number chosen here. So this is the SYN segment, the first segment, and we see some long sequence number, 2415.108. Remember, sequence numbers are 32-bit values, and the source or the computer chooses a value normally so it's different from the previous values it's used. So in this case, it's chosen this long number. And the flags, Wireshark shows us a summary, and then in the detail we see, remember, the flags are just 1-bit values. If that bit is set to binary 1, it means that flag is on or set. So in this case, there are multiple flags. Only one of them is set. The SYN flag is set. The ACK flag is not set, urgent. The other ones that we haven't discussed much are not set. So they're just 1-bit values there. Let's just record what that sequence number was so we can just check everything works as expected. So A, or my computer, sent to the server B some SYN segment, and the sequence number, I will not write it down, 241566. Let's just write down the last 4 digits, 6108. Okay. The next segment. The SYN flag is set and the ACK flag is set. It's a SYN ACK. And the sequence number is this other long value, 1901. Let's write the last 4 digits, 8124. And the ACK number is one more than the sequence number chosen or sent in the first message. If you compare that to the one up here, here we ended with 6108. This ACK number is 6109. it's acknowledging this sequence number that was chosen by computer A. And we see in the third segment the final ACK. ACK is set, ACK number 8125. So that's our three-way handshake to set up the connection. And one more, the first piece of data coming from computer A to computer B. We can see the sequence number. So this is, sorry, this is the data coming from A to B. From TCP's perspective, it has sequence number finishing 6109. That's what we expect. We chose 6108. B said, I now expect 6109. That is the sequence number in the first piece of data. And what is the data? The data shown here in Wireshark is the HTTP message. So we can expand and see the data from TCP's perspective is 301 bytes. It shows down the bottom of Wireshark that what's inside here is 301 bytes. So although it's not a field, we say the length here is 301. We can expand and see what the actual data is. It's our GET request with some options, so it's requesting a web page. And an ACK is going to come back, and the ACK number is going to be again 6,410. The sequence number is 6,109. The data contains 301 bytes, so we can think this data goes from 6109 up to 6409. So the next would be 6410. Simply the sequence number plus the length in this case. Is it? Yes. If you look up, where's my pointer? This one, 6410. So there's the ACK coming back. And you can follow through for the other messages and see that what we've captured here is just these sequence numbers of the TCP segments. 6410 is the ACK coming back. And the data coming in packet 6 from the server to my computer uses a separate set of sequence numbers. It's starting from 1901, so on 8125, independent from data going from A to B. So that's another example showing our TCP data transfer. Any questions on the basic data transfer? If there's no errors, the next thing we need to cover, what happens if something goes wrong? That capture is on the website. It's from one of our first lectures this semester. But you'll see the same in the wireless LAN capture you did for the assignment. The last thing we're going to cover with TCP is the very basics of how we retransmit error control. TCP uses, from our perspective, a selective retransmission or selective reject ARQ scheme. Remember when we looked at error control after the midterm, we saw there was stop and wait ARQ, go back N, So stop and wait, we send one segment, one packet, stop and wait for an ACK, and if we don't receive an ACK, we time out and retransmit the data segment. Then we had the sliding window extension where we allowed the source to send multiple segments, and there were two variants, go back N and selective reject or selective retransmission. In go back N, we send multiple segments. If we lose one, so we don't receive an ACK, then the source has to go back and retransmit all segments it has sent since that lost one. So if we send 10 segments, if the fourth segment is lost, in go back N, we need to go back and retransmit the fourth, fifth, sixth, and up to the 10th segment. Whereas with selective reject or selective retransmission, we just retransmit the one segment that was lost. More efficient, but with selective reject, it's more complex at the receiver because we need to store some segments in the memory, in a buffer. So there were two variants, go back N and selective reject or selective retransmission. TCP uses selective retransmission. We send multiple segments. If we lose one, we go back and retransmit that one. We have ACK numbers. They will indicate the next in order sequence number expected. We expect to receive data in order. And what the ACK number will say is, once we've received data successfully, the ACK number will indicate the next value expected. Even if we miss one segment and receive later ones, the ACK number will indicate the missed bytes that were received. We'll see an example shortly to make that clearer. Because it's selective retransmit or selective reject, the receiver needs to buffer some segments and put them back into order once we receive the retransmission. And as before, we send data. If we don't receive an ACK, we may time out and retransmit. So we expect an ACK to come back. If we don't receive one within some time, resend that data segment. We may have cumulative ACKs. What that means is we don't have to ACK every data segment received. It could be send two data segments, receive one ACK for both of them. So that ACK indicates that two data segments have been received. So it's more complex than just one ACK for every data segment. And we'll see that there is a way to optimize, but we'll go through the basic retransmit first. So here's an example where host A has, in this case, six data segments to send to host B. Let's keep track of what's sent and received. So host A has 6 data segments. In this example, just for simplicity, each segment contains 1,000 bytes of data. And the initial sequence number was 0, and therefore the first byte is 1. So if we drew those segments, let me draw them differently. We have 6,000 bytes of data. They're divided into 6 segments from 1 up to 6,000. So when we send the first segment, the sequence number will be 1. The second segment will be sequence number 1001 and 2001, so on. They will be the sequence numbers included in the header. That's a 6,000. This is the last byte. first byte. And that's shown in simple form here. To make it clearer, I've shown it on to the left of the host A vertical line. So a data segment with sequence number 1, a data segment with sequence number 1001, and so on. And assume that every time we send a data segment, after we've transmitted, we start a timer. We start our stopwatch to count and wait for an acknowledgement. If we don't receive an acknowledgement within some reasonable time, we'll retransmit that segment. That reasonable time is defined, it's our timeout period. So it's part of the protocol, or it's selected by TCP. So let's go through and see what happens in this case. We've got 6 segments to send from A to B. Remember, we have a sliding window mechanism allowing us to send multiple segments before having to wait for an ACK. We don't have to wait for an ACK after each segment. So we send our 6 segments, 1 through to 6. The first segment is going to be received successfully, so is the second. In this example, the third segment is going to be lost. Something goes wrong in the network, in the internet, and it doesn't get delivered to the destination. Let's see what TCP does. When B receives the first segment, let's record what B has received, the data. When it receives the first segment, that contains 1000 bytes of data with sequence number 1 up to 1000 with 1000 bytes. Therefore, B sends back an ACK saying the next byte expected is 1001. Okay, because B has just received the first 1000 bytes, it now expects 1001 as the next one. Then slightly later, it receives the next segment. That next segment contains bytes 1001. There's the sequence number 1001, and it contains 1000 bytes, so that will go up to 2000. And therefore we send back an ACK with ACK number 2001. The next one expected is 2001. Then, slightly later, B receives another segment, the third segment. What does it contain? It contains bytes 3001 and up to 4000. And B recognises something's gone wrong here. B expects to receive the data in order. It receives the first 1000, the second 1000, and then it's expecting to receive 2001, but it doesn't. It receives a segment with sequence number 3001. Because one segment has been lost in the internet somewhere. B is, of course, not going to receive that. So the ACK number that goes back, so we can still send an ACK here, but the ACK number indicates the next in order value expected. B has received 1 up to 2000, it's still waiting for 2001. And that's where we see the ACK number 2001. Even though it's received this, what is the fourth segment in the sequence, it's still expecting the third segment. And it informs A by sending an ACK indicating I'm waiting for 2001. It still stores this segment it received, stores this in memory, but waiting for this missing one. And another segment's received, sequence number 4001, going up to 5000, 1000 bytes. But again, the ACK number is 2001 because we're still missing something from B's perspective. And then the last segment. And that final ACK here. There was no more data sent, so B's not going to receive anything. It's still waiting for segment starting with sequence number 2001. Now, coming back to A's perspective, it sent 6 segments. After sending each, it starts a timer. And it's waiting for an ACK. It receives an ACK indicating sequence number, or ACK number 1001, which acknowledges the first segment. How does it know that? Because when we sent that first segment, we knew it went from 1 up to 1000. Therefore, when we receive an ACK number 1001, it means those bytes from 1 up to 1000 have been successfully delivered. So this ACK, the ACK number, implies that the first segment has been successful because the first segment contained bytes 1 up to 1000. So everything's okay. That happened before our timer expired. Then we receive another ACK saying ACK number 2001. This implies all of our bytes up to 2000 have been successful, i.e. the second segment has been delivered. Everything's okay. We're waiting for an ACK. We receive some more ACKs. So the first ACK implies from A's perspective that the first 1000 bytes have been delivered. The second ACK implies the second 1000 bytes have been delivered. But then we receive an ACK with ACK number 2001 again. So we don't know if our other data has been delivered. We only know that the first 2000 bytes have been delivered from these 3 ACKs. And we're still waiting for an ACK. We'd expect to receive an ACK for those other segments we've sent. We're waiting for this third segment which was sent, starting with sequence number 2001. We haven't yet received an ACK number greater than 2001. We're waiting for an ACK. We time out. We've waited too long, so some timer expires, and that triggers the source to retransmit that one segment. These two have been successfully delivered. We know that from the ACKs. We haven't received an ACK for the third one. We time out, so we retransmit that third segment. Retransmit this one. Any questions so far? We'll see what happens when B receives that. Okay.
How about the last 3, the last 3 segments? Do we have to send back the ACK back?
So from B's perspective, these 3 segments, it receives them. It sends back an ACK, but note the ACK number is not really acknowledging those segments. It's just saying, I'm still waiting for 2001. So from B's perspective, it stores the data in those segments. It stores them in memory in a buffer, but it's still waiting for 2001. And it tells A that. And it keeps telling A that by sending back an ACK. I'm waiting for 2001. When A receives them, well, at this stage they're of no use because A knows that the up to 2000 have been successful. We're expecting an ACK for 2001 and beyond. We haven't received that, so we retransmit here. We'll see that they become important in some optimization. Let's finish this case. Retransmit. So this is segment with sequence number 2001, the third one that A sent. Resent. B receives that segment. That's this one, containing sequence number 2001 up to 3000, 1000 bytes. And now B has received sequence numbers 1 up to 6000. Next value expected is 6001. And hence it sends back an ACK with ACK number 6001. So from B's perspective, it has now received all 6,000 bytes and just waits for more data to come. So because it stored these 3 segments in memory, once it received the one that was missing, it now has 6 in order and now can move on to waiting for the next piece of data to arrive. And when that ACK comes back, it acknowledges all of these 4 segments. Because when the ACK comes back, it has ACK number 6001. When A receives that ACK number, it knows that B has received data up to 6000. So if we receive ACK number 6001, it implies everything up until 6000 has been successful, which is, from A's perspective, these 4. So this one ACK effectively acknowledges these 4 segments. It's a cumulative ACK. And now A knows it has sent 6,000 bytes and those 6,000 bytes have been ACKed. And B has received those 6,000 bytes. And now we can move on to more data in the future. So this is the basic retransmission scheme of TCP. It's a selective retransmit in that we only had to retransmit one of those, that one lost segment, not the subsequent ones. We didn't have to retransmit these 3 segments. In go back N, we would. We've got one more slide for TCP before we do that and finish this topic. Any questions on basic retransmit? The default means for retransmitting in TCP. There's an optimization. There's a way to improve the performance of this. The problem with this approach, and the problem with any timeout, is we have to wait a long time before we retransmit. That could be inefficient. We would like to retransmit earlier. And we can do that, and we use this extra rule, which is illustrated in fast retransmit. Same scenario. In fact, let's even leave it here. With TCP fast retransmit, there's an extra rule that says if we receive 3 duplicate ACKs, that is 3 acknowledgements with the same ACK number as what we've received previously, then that indicates something's gone wrong. We see what happens here. B sends ACK number 2001. A receives that, everything's okay, that's expected. But then B sends ACK 2001 again. A should be expecting ACK 3001, or at least greater than 2001. But we receive the same ACK number again. So let's say it's a duplicate ACK. And then we receive it again. And a third duplicate ACK. That is 4 ACKs with the same ACK number. That makes A think something's gone wrong. I know I have sent data with sequence 2001. I've also sent some other segments, subsequent segments, but now I'm receiving 4 ACKs all with the ACK number, the same ACK number. That indicates to A something has been lost. In particular, the segment with sequence number 2001 has been lost. When we receive this third duplicate ACK, then now A immediately retransmits that segment. And that's shown in fast retransmit. Same scenario, we still have a timeout. So if the timer expires, we retransmit, but there's some extra condition. If we receive 3 duplicate ACKs, in other words, 4 ACKs with the same ACK number, then retransmit. So we'd retransmit our data here and then receive the final ACK. The difference is we retransmit earlier in most cases. With basic retransmit, we wait for the timeout to occur. With fast retransmit, we either wait for the timeout to occur, or if we receive 3 duplicate ACKs, we retransmit. And in many cases, we will receive 3 duplicate ACKs before a timeout occurs. We'll spend less time waiting before we retransmit. It can be more efficient. So fast retransmit, it's faster to retransmit because of a lost segment. The advantage is that we can improve the efficiency of performance by retransmitting earlier than if we waited for a timeout. It's not always the case. There are some cases where it will not benefit, but in most practical cases, receiving 3 duplicate ACKs will happen before a timeout occurs, and we can improve the performance. If we don't receive 3 duplicate ACKs, then we still wait for a timeout. If a timeout does occur, they will still retransmit. So it's a small optimization which can be quite useful in practice. A couple of minutes for questions. Yep.
Why does it have to wait for the third duplicate ACK? Why can't it just wait for the first one?
Okay, so why wait for the 3rd duplicate ACK? Good point. Why not wait for the 1st and retransmit, or the 2nd, or the 4th? Well, it's decided that most likely, if we receive 1 duplicate ACK, then it's possible that maybe this segment has been delayed a little bit. If we receive 2, then it's more likely that it's been lost. If we receive 3, it's even more likely it's been lost. If we receive 4, it's even more likely. So it's just a trade-off in that the designers have said that, okay, 3 duplicate ACKs is a reasonable trade-off in we expect to receive them quickly, and it gives us a high enough likelihood that a segment has been lost. So in theory, it could be any number of duplicate ACKs, but a practical trade-off is 3. So that's what's used. So in all normal TCP mechanisms, it's 3 duplicate ACKs, or 4 ACK numbers the same. Any other questions on either the basic retransmit or fast retransmit?